All right, a very good morning to all of us as we look into part two of electromagnetic induction. So the previous chapter we talked about Faraday's law and Lenz's law. So now we would like to introduce how we can actually use this in AC generator. This is different from your DC motor. This is a AC generator. So please make sure that you understand the concept of DC motor first before you come back to view on AC generator. Okay. Uh, One important application for electromagnetic induction is for the generation of electricity. So we can generate electricity using this method. Uh, the main idea here is to transform mechanical energy into electrical energy. So the mechanical from our previous chapter is that you can see that the mechanical comes from the part where we force the magnet or when we move the magnet. Okay, and then we will generate electricity, which is the induced EMF or induced current. So a simple AC generator will look as such. Similarly, you have your magnets, north and south. You have a coil. These coils are connected to two slip rings also, and two carbon brushes, and then this is connected to anything that you want to power. Okay. At the same time, you need to exert a force to actually move this coil in this setup. So let's explain how this works. So when the coil of wire ABCD, or what we call as an armature, ABCD, this coil is rotated. So when you exert a force to rotate it itself, there is a change in the magnetic flux in the coil. So the magnetic field that is generated by two magnets will actually be cutting the coil, and then the amount that's going through the coil will vary. Okay, so example, if you have a magnet here and then you have a magnet here, north, south, as your coil moves, okay, if these are the few lines moving from north to south, you realize that the portion that I will highlight here in blue are the magnetic field that is cutting across this coil. So the amount of magnetic field cutting across will change as your coil turns around. So when there's a change of magnetic flux, because when you have a change in magnetic field cutting through the coil itself, there is a change in magnetic flux. So when there is a change in your magnetic flux itself, there will be an induced EMF. So let's come back here. So when the coil rotates, there is a change in the magnetic flux. Keyword here is the change in magnetic flux in the coil. What will happen is this induces an alternating EMF between the ends of the coil, and this induces an alternating induced current in the external circuit. So it's exactly the same as in the previous part that we talked about, just that now we use a coil instead of a solenoid. Okay, so remember, as the coil turns around, this coil, the area itself, will actually cut more of the magnetic field. So more magnetic fields will go in, there will be a change in magnetic flux. Okay. So do not be confused with the split rings used here as compared to the DC motor. Remember, in your DC motors itself, the split rings are half split rings. So they're split into half to change the direction of the current every 180 degrees rotation. Whereas the split rings here for AC generator, different, is to allow the armature to be turned continuously without the wires in the external circuit being tangled. So you don't have to split the ring into half as compared for your DC motor. Okay. All right. So take note that the split rings are different for DC motor and for AC motor. The DC motor split rings are half split rings. They are used to change the direction every 180 degrees rotation, whereas the split rings for the AC generator is one full circle, and it's just to allow continuous connection with the external circuit. So this is what happens. This is your coil AB. So how do you view it itself? Can you see there's an A and the B here? If you look from the front here itself, okay, this is your eyes. You look from the front, AB will be like that. This would mean when AB is like that. Okay, and so on and so forth as it rotates. Okay, so as it rotates itself, there will be an EMF produced, and this will be the graph of how the EMF produced along with time as the coil actually rotates. If you realize some of the EMF is positive, some of the EMF is negative, this shows the alternating nature of the EMF, and as such, the alternating current being induced. So notice that the maximum EMF, which is E0, this is the maximum. when the side AB is parallel to the magnetic field line. So your magnetic field lines is here, north and south. So this is the magnetic field lines. Okay. So in this case itself, your magnetic field lines is from north to south. If the side AB is parallel, so you can see this AB is here, magnetic field lines is here. If they are parallel, this is when there is maximum EMF. Okay. Why this? Because the sides AD and BC, A, B, C, D. So AD, this side here and this side here itself, cuts across the magnetic field lines at the greatest rate. So the amount of magnetic flux that it has that changes over time increases. So since the rate of change of magnetic flux is maximum, the magnitude of the EMF will also be the maximum. So this happens when it is parallel. So what happens when it's the other side? Then it will be at a negative maximum EMF. Okay, the induced EMF is zero when the coil is perpendicular, as in here, 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 and here. When their coil is perpendicular to the magnetic field lines, this is because side AD and BC do not cut across the magnetic field lines at all. As such, the change of magnetic flux will be very, very little or none at all. So since the rate of change of magnetic flux is zero, the magnitude of the induced EMF is zero in this case. Okay. So if at any point if you're confused, please go back to the front again and then recap on this, or you can read your textbook. From the previous chapter of general waves itself, how is the relation of frequency related to the period? We know that F is equal to 1 divided by T, or the other way around. Okay, we know that there's this relation. So if we were to double the frequency of rotation, that means you turn it faster. If you turn it twice as fast, the time taken for one complete revolution or rotation will be half, because you turn it twice as fast. So the one rotation or revolution will be half the amount of time taken. So example, if you take 4 seconds previously to turn one round, now you halve it, you spin it twice as fast, now you only take 2 seconds, which is your period. Okay, because the turning is twice as fast, the energy that we supply is also twice as much. Because you want to turn it faster, you need more energy, remember? So since the energy is more, hence the output will also be twice as much. So let's start again. Because we turn twice as fast, we need more energy. Energy is twice as much, that's why the output will be twice as much. When your output voltage, your output induced voltage is twice as much, so your EMF maximum will be higher. Okay. At the same time, the lower one also will be higher. What else there? Because you turn twice as much, remember that this is a period in your x-axis. Okay, so since it's twice as much, originally this is your amount of time needed for one revolution, but because now you're moving faster, we now look at this line here. Okay, so now you can see that your wave is half the duration. So what do I want you to notice here? There are two things that I want you to take note here. Number one, when you spin it faster, or when you spin at twice the frequency, your EMF doubles. At the same time, your wavelength here will also have to be, it will take a shorter period of time. Okay, so these are two things to take note of when we draw the EMF time graph. So how can we increase the induced EMF for this AC generator? Increase the number of coils, number of turns on the coil. So where is the turns? This is 1. You can increase many more and put around it. Okay, that's the number of turns. You can also increase the frequency of the rotation. So now you want to spin faster. Remember, when you spin faster, twice as fast, your maximum EMF will also increase. You can use stronger permanent magnets. So the magnets that you place, you can use a stronger one also. And at the same time, you can wind the coil on the soft iron core. Why? This will strengthen the magnetic flux linking to the coil. So what do I mean? Put the iron here inside. Put iron here. And then you spin it along, because this will help to concentrate the magnetic field lines inside there and will help to strengthen the magnetic flux linking the coil. All right. So these are the 4 ways to increase the induced EMF of an AC generator. So let's look at an example. So when the coil rotates 5 times per second, we know that there is a frequency of 5 Hertz. And induced EMF with a maximum value of 40 MV is produced. So what is the period of rotation? T equals to 1 over F. There is a formula. Write down the formula first. Then it is 1 divided by 5 Hertz. Because the frequency is 5 Hertz, you get a period of 0.20 seconds. So when the rotation is reduced to 2.5 times per second, so now you half the rotation, you half the frequency. They want you to say, sketch the graph of EMF on how they actually change. So when you half the frequency or half the rate of the rotation, your maximum induced EMF will also half, and your period will double, because now when you half your frequency, okay, your period will be 2 times. How do we know? Just use the formula T equals to 1 over F, and then you will understand why the period is 2 times longer. So when we draw it itself, this purple color is the original EMF time graph. So we know that your EMF will be half the maximum. So now we use at only 20. So all the maximum must be 20. And we know that the period must double. So originally one of the period is from here to here. Now you got to increase it all the way here. So your period now must be double. So this line, the thin red line, will be your new EMF time graph that is being produced for this AC generator. Next, when we design an AC generator itself, there are a lot of practical means. We cannot just use whatever we have learned like this setup here itself. Because in this setup, let me clean this up. In this setup itself, it may not be practical for every situation. So let's take for example, in the real world use itself, instead of rotating the coil of wire, now we rotate the magnet. So we keep the coil fixed and then we rotate the magnet. This is known as a fixed coil generator. In this case, we will not require slip rings. We will not need the carbon brushes because now the coil is not moving. We are just moving the magnet. Okay. So how is it like? Example, in your bicycle dynamo, what we have is a magnet that is rotating. So this thing will spin. Your magnet will turn. We keep the coil fixed. Okay, so you don't need slip ring, you don't need carbon brushes. What is the advantage? There is no need for carbon brushes. These carbon brushes will have wear and tear and then need to be replaced. As such, it's cheaper. So if you don't need carbon brushes, it's cheaper. Next is less likely to break down from overheating. Why? Because if you do not use slip rings and carbon brushes, there will not be a connection, because this connection between the slip ring and carbon brushes will increase resistance and will generate heat that will result in energy loss that will cause wear and tear, cause overheating, you waste energy also. Next, the fixed coil generator is more compact and space saving, and as such more practical. Example, the bicycle dynamo, as you can see here. So a dynamo is basically to use the tire movement to generate electricity, and this electricity can be used to power whether it's the light or used to power any other electrical devices. Okay, so with that we will end this section on AC generator. Thank you.